Okay, so what I'm going to talk about now is somewhat of a different different notion. It's not a commonly it's not a common algorithm to discuss in a course like this, but I think it has connections to many things that we've seen so far, and it's actually a very contemporary sort of hot topic in theoretical computer science, and this is the notion of what's called electrical flow. So let me motivate this by the things that we've done so far. Let's look at max flow in an undirected graph. Sort of the classic problem, and we want, sort of near linear algorithms. So there are polynomial time algorithms, but we want near linear algorithms, especially for sparse graphs. And there have been recent advances in that which use a different kind of flow that I want to talk about. So it's convenient to think of it differently. Let's just think of feasibility. We want to check if the max flow is greater than some f. Just determine if it's greater than f, then we can do binary search. So here's our graph, here's S and T. So instead of this, I'm going to scale down the problem. I will scale the problem, scale down by f. So I'm going to just scale it down, say I want to send 1 unit of flow from S to T, where the capacity of an edge has now been scaled down. So what I can say is I want the flow on the edge to be at most CE divided by f, because I've scaled everything down. Okay, does this make sense? I want to send 1 unit of flow from S to T, where the flow is now going to be the capacity divided by f, because I scaled the problem down. Okay. I can think of this in another way, which is consider what I'll call the unit flow polytope. So the unit flow polytope is basically how many ways can you send 1 unit of flow from S to T. So all this is saying is that x of, I'll say, delta V is equal to 0. So this is basically just saying that flow out of V is 0 for V not equal to S and T, and x of delta S is equal to 1, and x of delta T, this is the flow going. So this is the flow going outside of S is 1, the flow going outside of T is minus 1. Okay, this is flow conservation. And so this gives... Yeah.
So I have a question.
Yeah.
Sorry.
Yes.
So by scaling down by f, we does not change the distribution of the flow, right?
No, it doesn't. Right? It's just like dividing everything by f. Exactly. So this is some polytope. Yes.
So the total flow gets to 1, right? And the distribution still holds. Okay.
Yes.
Okay.
Yes.
Got it.
Yeah.
Sorry.
Yeah. No. So this is a convenient representation because now I can think of the problem differently. So here's the flow polytope. This is some flow polytope. And what I want is a point in the flow polytope that satisfies these constraints. So you can represent these constraints as some kind of a box. Right? These constraints are given like a box, and you want to see, is there a point in the intersection of these polytopes? And so one can think of this as an L infinity constraint on X. You're looking for a point that satisfies some L infinity constraint on X, some point in the flow polytope that satisfies these constraints. And of course, X is greater than 0. Okay, any questions about this formulation? And so in general, in optimization, L infinity constraints are typically hard to deal with. And so you have a norm constraint. What is the norm constraint you should look at? What is the most natural norm constraint to look at? Anyone? What is, like, when you talk of norms, what norm do you think?
Euclidean norm.
Euclidean norm. So we could say maybe it makes sense to think of Euclidean norms instead. So instead of trying this, suppose we try to minimize the Euclidean norm. So we find a point in this polytope. So this is the flow polytope P. Find a point which minimizes some kind of a scaled Euclidean norm, which is actually related to an ellipsoid. But instead, suppose we did the following. We want to minimize summation over all E of xe squared, and instead of, saying that xe has to be less than this, I can give some kind of penalty for edges with lower capacity. So what I could do is I could try to minimize something like this, xe squared divided by ce squared, and check whether, I can get my constraints. So this is just, I'm just telling you an idea that someone might have. And it's convenient instead to give something called the resistance of an edge. So I'll call this the resistance, which I'll just set to be 1 over ce squared. So an edge with high capacity has low resistance. An edge with low resistance has a high capacity. And what I want to do is I want to minimize this quantity. Xe squared times Re. And now I can look at solving this problem on the flow path. Minimize this, and of course then you have, x of delta V is equal to 0, x of delta S is equal to 1, x of delta T is equal to minus 1. This problem actually has faster algorithms, which itself was a fairly big breakthrough in the past 20 years. And those fast algorithms have actually led to fast algorithms for approximate flow. So this has been a very ongoing development over the past, I'd say, 5 or 6 years. What I'd like to talk to you about is this electrical flow and really some beautiful connections between this and optimization. Okay, so I'm going to write this out now maybe in a little bit more detail. So what are the constraints that I have? I can say, okay, for all V not equal to S and T. So for convenience, I'm just going to order the vertices. I'm going to order the vertices from S to T, and I'll just order them arbitrarily. It doesn't really matter. But I'm just going to think of edges. Edges are undirected, but just think of them being directed from I to J. This is just going to be convenient for me. So order the edges and direct edges according to the ordering. The graph is undirected. It's undirected. But this is going to be convenient. It's going to cut down the number of variables that I have. Otherwise, I have to think of the flow going in one direction is the negation of the flow going in the other direction. And I can just directly deal with that as follows. So I'm going to think of the flow. Okay, so now here's my graph. And I'm going to think of flow being potentially even negative. So if I have I less than J, positive flow goes from I to J. Negative flow is going from J to I. So this is just going to cut down the number of variables I have. Okay, so for all, and you'll see why this is going to be convenient for something I'm going to do. So for all V not equal to ST, what we have is the summation of U in the, I'll write this as the in neighborhood of V of X UV minus U in the out neighborhood of V of X V U. This has to be 0. And then I get my usual constraints of the summation of U in the, so S only has an out neighborhood because S is the minimum in the ordering. X SU is equal to 1. And then you have some constraint for T. Right, involving T. This is a constraint for S, constraint for T. and this is the objectives. This is not a linear program. This is a convex program. I'm going to tell you about something called the Lagrangian, which is essentially the same notion of duality that we've dealt with, but really the general notion is the way to solve an this is a constrained optimization. And so what we can do is we can introduce dual variables, and these are also called Lagrange multipliers. So we can introduce dual variables, and the dual variables, so we're going to have a dual variable of, I'm going to refer to these as y. So we have ys corresponding to this constraint, yt corresponding to this constraint, and then we have the yv's corresponding to that constraint. And so what we get is, the nice thing is I'm going to write down something here. So this is the original objective, plus I'm going to add the Lagrangian term. So I'm going to sum up for every constraint v not equal to s and t. I can take yv times basically that constraint. So summation u in n minus of v x uv minus u in n plus of v x vu. For convenience, and you'll see why this convenience appears, I'm just going to multiply this by a half. Okay, I'm just going to say that I want to halve this expression. This is not going to be that important. It'll be convenient though. Plus, I have ys times I'll do 1 minus the summation of u in n plus of x s u plus yt summation of x u t, u is in the neighborhood of t, minus 1. This is the Lagrangian. What is nice about the Lagrangian is that, so I'm going to refer to this entire function as fx lambda, fxy, I'm sorry, fxy. Primal? Dual, fxy. So what we wanted was, what you can show is that what we're looking for is, I'm going to use technically infimum and supremum because these are continuous. What we wanted was the infimum of feasible x of this quantity. This is what we wanted. It turns out this is equal to the infimum over all x, so it's unconstrained, of the supremum over y of f of xy. Can you see why this is the case? And once you see the argument, it's actually quite clear. Once you see the argument. What happens if you chose an x that was infeasible? What happens if you chose an x that is infeasible here? Actually, let me state that here. Suppose you choose an x that's feasible. What happens to these things? What happens to these things? Anyone?
All zero.
They'll all become 0, exactly. Excellent. So for a feasible x, the Lagrangian is the same as the original. When you choose x that's infeasible, what happens to these? Right? One of them is non-zero. What's going to happen then? what would you set the Lagrange variables to be? Because what would you set the dual variables? You're trying to compute the supremum here. So what would happen if you choose an x that's infeasible? What does the supremum become? If this is non-zero, and you're trying to maximize the value of this by setting y's, you can set y to be whatever you want. What would you set y to be? What could you set y to be? Suppose this was strictly greater than 0. What would happen?
This is unbounded then, right?
Exactly, it becomes unbounded. So the supremum becomes, so supremum basically doesn't exist, and therefore if you take the inf of the supremum, you get rid of anything that is infeasible. So for any x that is infeasible, basically this Lagrangian, when you take the supremum, I mean, I think this is also referred to as the Lagrangian, like the supremum of y. The supremum of y basically becomes unbounded. Hence, if you take the infimum over all x, you exactly only look at feasible. Okay, so the proof is an exercise. But that's the idea. When x is feasible, then this is exactly the same thing. When x is infeasible, the supremum is unbounded. Okay. Next is a lemma that the infimum over x of the supremum over y of f of xy is greater than the supremum over y of the infimum over x f of xy. This is called weak duality, which you all know by now. And the proof is also quite easy. The proof is actually, it's the same thing as the weak duality proof. I mean, actually, if you remember, for von Neumann's Minimax theorem, it's essentially the same argument. So I leave this proof as an exercise. Right? You switch the inf in the soup. Right? And you can think of it as whichever player plays first gets an advantage. Or whichever player plays second, I'm sorry. Whichever player plays second gets an advantage. So because the supremum player is kind of like playing second, gets an advantage over it. So this is, and what we actually have is main theorem of strong duality, and this is von Neumann's Minimax theorem, is that actually this is equal. This is equal because, okay, so I should, let me write this and then I will say, these are equal because this is convex and these are linear. So when it's only because there's a relation, because this is convex and these are linear constraints. Like if it was arbitrary, this would not hold, but this is, biconvexity. Okay, so why am I doing all of this? I wanted to solve this original problem here of basically trying to find a flow that minimizes this sort of Euclidean norm or the scaled Euclidean norm. What I end up with is this Lagrangian formulation, and in the Lagrangian formulation I'm looking at the supremum over all y of the infimum of all x. Now let's do some math here, and we will discover something that is quite remarkable. Yes.
Can I ask a possibly stupid question?
Go on.
Why, like, how exactly is the Lagrangian corresponding to duality? I don't see the connection. Like, is it just by definition? Like, do we just treat the Lagrangian as, like, at least it doesn't make sense to me in terms of how I see duals so far, like how I've seen duals for LP.
Actually, this is the theory of duality from which, if you followed this, you can recover the duals as we defined. the dual variables are exactly the Lagrange multipliers. Like you can write down a Lagrangian for linear constraints where this would be linear and these would be linear. And then you would take an inf and sup and you would switch them by strong duality. And then you will do some calculations on this to say that, well, okay, for any y, what is the inf going to look like? You will do some calculus and you will recover the dual.
Okay, so is this like a grand theory of duality that
I mean,
for all?
In optimization, this is duality. And LP duality is a special case of the Lagrangian duality. I don't know if that answers your question, but what were you looking? I mean, maybe. So you're saying
I just don't see, like, I couldn't reconcile this treatment with what I've seen so far. But if this is where you start and then go there, then that makes sense.
I mean, I think that what you maybe need to step away is dual in the linear algebraic perspective.
I shouldn't look at it that way.
I don't think that is valuable in this from this perspective. No.
Yeah, because that one actually makes sense from the linear program point of view, but here
I don't think that you should think of like that end up being a consequence of this more. Okay, so far so good. Okay, so now what do we have? We have this supremum of the infimum, and we know that if you took x star y star optimum, then there's sort of this min-max pair, right? So then let's choose an x star y star optimum and try to understand what are the relationships we can get between them. So we know that the supremum over y of the infimum of x, fxy, this is actually equal to fx star y star. So in this case, the supremum infimum actually exists, so I can do max and min. So we know that this is the case. So we know that for y star, x star is the minimizer of fxy star. Right? X is basically the minimizer of fxy star. And you know, fxy, you know, it's not a horrible expression. So what you can do is by calculus, I mean, okay, technically you have to take second derivatives and other things like that, but you know it's going to be a stationary point. So you know that for all edges E, you can take the derivative with respect to E. Okay. So for all edges E, you know the derivative, the partial derivative of fxy star with respect to dxe is 0. It's a minimizer. So you get this. Okay, so far so good. So I'm just taking the derivative. So I'm just saying that when you look at the optimal point, or technically when you evaluate this at x equal to x star, that is 0. The derivative is 0. Right? So I take the partial derivative with respect to xe of the Lagrangian when I plugged in the optimal dual, because I take the supremum and the infimum. Okay, so far so good. Any questions about that? Okay. So now let me work this out. Turns out this isn't really that bad. Let's go back to here. Where does xe appear? It appears once in the objective. So I'm just going to write that down. I'm just going to write it down over here. Okay, so I got half xe squared re. And let's just say that e is equal to u comma v. So it appears in this one term here. Plus it's going to appear in two terms corresponding to yu and yv. Okay, corresponding to yu and yv. And if you do it, you'll see that there is a term yv xe, because it is uv, minus yu xe. And you can, if the edge is incident to S as well, the same thing is going to happen. So every edge appears twice, once positive, once negative, depending on the endpoint. This is the expression restricted to xe. Okay, and you're going to take the derivative of this expression really, because this is what you care about. So I'm just going to write this over here. So this is just saying you're taking the derivative, the partial derivative in this case. You can ignore all the other things. So it's just d by dx dxe of this expression, half xe squared re plus yv star, because you're plugging in the optimal y, minus yu star xe. And this is equal to 0 for xe star. Okay, let me now plug this in and you see what you get. You get, the 2 will cancel out, so you get xe times re plus yv star, so remember E is equal to uv, minus yu star is equal to 0. Let me restate that. Xe times re is equal to yu star minus yv star. What does this mean? You've all seen this. If you've taken physics courses, you would have seen this. I'm just going to rewrite these. I'm going to call this IE. I'm going to call this phi u. So let me even not put stars. Let me write this out over here. IE xe. I'm just going to call this I, because it's a flow. That's like current. And let me call, I'm sorry, my apologies, I'm messing it up. I'm going to write this I. So it's IE RE is equal to, I'll call it capital V of u, or you can even call this phi. Sorry. So what is this? What is this expression that I've written here? It has a name. It has a name. IE is current. RE is resistance. So what is phi?
Voltage.
Sorry?
Voltage.
I didn't get that. Sorry, you broke up.
Voltage.
Voltage. So what is this called? What is the name of this thing? Current times resistance equals to potential difference.
Oh, right. Yeah. So,
what is it?
Yeah, but that is voltage, right?
Yes, that is voltage. Exactly. It is. So what is it called? What is it? What is the name of this?
Is it Ohm's
law? Ohm's law.
Oh, you meant the name of the law. Okay.
The name of the law. We have actually derived Ohm's law from energy minimization. I will let you ponder on that for a bit. We've actually derived Ohm's law using duality from the concept of energy minimization. I'm gonna write this
that's
up.
Heat.
Huh?
We are minimizing. So we are minimizing heat.
You're minimizing the dissipation of heat or power, right? Because I square E or X square I square RE. Like the square of the current and the resistance is the power. Exactly, you're right. It's the heat generated. So what we have derived is that minimizing heat is equivalent to Ohm's law. I mean, how amazing, that should blow your mind. This is like we have proven something deep in mathematical physics here. So I will restate that. What we want to do is we want to minimize, and I put a half over here, summation over E x square E RE. This is the energy. Energy or the heat dissipated. We wanted to minimize that subject to Kirchhoff's law, which is flow conservation. The nice thing about this setup is there's no talk of potential of voltage. This just talks about minimizing energy. But we derive from this the existence of potentials, related by Ohm's law. So this is actually a deep connection. In physics, what it says is that nature minimizes energy. The way to minimize energy, and so it's almost like I don't know, it blows my mind every time I think about this. Nature minimizes energy. Nature wants to send current to minimize the heat dissipated, which is like this natural conservation. The way that nature proves, so nature actually proves that she's minimizing energy by providing the dual variables as potentials, as voltages. This potential or voltage. So what is remarkable is that the voltage is really the dual variable of the optimization problem of energy. I mean, how amazing is that? And it all comes just from duality. Like von Neumann's Minimax theorem. You set up the optimization problem, you look at the Lagrangian, and when you look at basically the Lagrangian dual, and you basically do the calculus, you derive Ohm's law as a consequence of energy minimization. And actually this is equivalent. This is equivalent because, but by duality, the fact that potentials exist, the fact that you can measure potentials that give you the current, that fact that Ohm's law is true, implies that actually the minimum energy solution is the one that or rather it implies that energy is minimized by whatever nature is doing. It's pretty amazing, huh? Any questions about this?
Not this, but the same stupid question from earlier.
Which is?
The duality part of the Lagrangian. How I see the Lagrangian is that we take some function and we take the tangent of the function at some point and say that the optimal is reached. I don't understand how to relate this. We are taking a tangent, right?
Well, I mean, we're taking a tangent here. Yes.
So what is the dual? How do you define the dual here?
So think of it as so maybe think of it differently as you have a constrained optimization problem. If you had an optimization problem, then you would just take the gradient, set that to 0 and be done.
Yeah.
Your problem is that you have a constrained optimization problem. You want to replace it by an unconstrained optimization because unconstrained optimization means you can start taking gradients. So you kind of introduce the constraints into the objective. You introduce the constraints into the objective using these dual variables. Instead of thinking of it duality in terms of, let's say, a dual of, like a vector space dual, which I feel that's not the right picture to have. I think of it more in terms of game theory. So you have two players. One player is trying to minimize XE. The other player is trying to maximize. Or one player is trying to minimize an objective. The other player is trying to maximize. And they both have the shared objective. And so in this case, duality is really like game theory. So there's a player, primal and a dual, and they're battling against each other. And then what they have is some kind of equilibrium point. So if you think about it game theoretically, then maybe the word dual is just like there's this opposing player here.
I see. Okay, yeah, that makes more sense than what I had in mind. So
yeah, so I think of it more of, I think in the optimization perspective, it's useful to think of there being two players. One player is dealing with the objective, the other player is actually dealing with the constraints, but the nice thing is that the constraints and the objective are both on a same footing in this expression. They're both in some sense like combined into this one thing. So instead of thinking of the constraints as something, you fix the constraints and you try to increase your objective, you want to combine them both together where you're actually allowed to violate constraints, and that gives you this sort of setup. But you know that by doing the Lagrangian, you still maintain your optimum. And then you look for min-max theorem. So the fact is you always have weak duality. So you should think of it, this is a mechanism to give you lower bounds on your objective when you're minimizing. And
right.
so this,
actually, like following up on that last point you said, like this form of weak duality that you mentioned here, that's actually true for all functions.
It's true for all functions, exactly.
Because soup is smaller than in soup is standard.
Yeah.
So are you saying that the strong duality condition is the one where you need convexity, like that falls through if you don't have a convex body?
Exactly, yeah. If things are ill-behaved, then you won't have this. Typically what you need is that, you need that f is convex with respect to x and concave with respect to y. Like if you have this sort of convex with respect to one and concave with respect to the other, then you get it. And in general, there is something called the KKT conditions which tell you when these things happen. And then there's also a notion of complementary slackness. Complementary slackness exactly is the same thing of, either this is going to be 0 or this is going to be 0. And you can easily get complementary slackness when you use strong duality and you put weak duality together. So you can think of this as like the underpinning of that theory. And actually it comes from game theory rather than, let's say, linear algebra duality. The game theoretic perspective is there are two players, one is trying to maximize, one is trying to minimize, and they have, this sort of shared objective. And that's what it is. But to me, sort of the amazing thing here, at least if you think about it from a physics standpoint, is really that this actually gives you an equivalence between two different views of current. One is through Kirchhoff's law and Ohm's law, the other is Kirchhoff's law, which is just conservation and energy minimization. And the fact is that these are equivalent. Okay, any questions? Okay, so now that we have that, let me now give you another nugget. So what we can now do is, if we want to solve this problem, instead of trying to just solve the primal problem, we now have Ohm's law that we can use to now solve the problem. So how are we going to use Ohm's law? And indeed, let's kind of write this out as what we have is for every edge uv, here's what we want to solve. You want to solve Ohm's law. Yu minus yv is equal to xe re. Right? So current times resistance is equal to the potential difference or the voltage. Now by Kirchhoff's law, what we know is that, and this is for v not equal to st, what we have is that if you fix, so if you sum over all u in the neighborhood of v of the currents, then you should get 0. We can write this as the summation of yu minus yv times 1 over ruv is equal to 0. This is for v not equal to st, and of course if you look at s, then you can say for all u in the neighborhood of s, ys minus so ys minus yu times 1 over RSU. This is equal to 1 because this is the current coming out of S has to be 1, and then similarly you have something for T. You have another equation for T. Let's write down these equations in matrix format. Let's write down these equations in matrix format. If you look at this equation, so I'm just going to rewrite this equation here. So this is the sum over all of this. What you get is the summation over all u in the neighborhood of I'm sorry, I'm probably fudging this up. Let me write this differently. YV minus YU. Right, so this is the current. I'm thinking of potential difference, right? So if YU has a higher potential, then there is current coming out of YU. V. Yeah, okay, good. So you have this. So we can write this as 1 divided by RUV times YV minus the summation of YU divided by RUV. And this is equal to 0. So let me now put this in matrix format. So here's my matrix. Let's look at this being one of the rows, right? So what do you have on the diagonal? So this is for V, right? This is a constraint for V. So this is a constraint for V. This is going to be a square matrix because you have exactly n constraints, one for each vertex, and you have n variables, one for the potential. So this is an n cross n matrix. Great. So over here you have the summation of 1 divided by RUV. U is in NV. And now for any U, what you have here is minus 1 divided by RUV. That's the matrix. This matrix is symmetric. It is also called diagonal dominant. It's called diagonal dominant because the diagonal entries are more than the sum of the row. The diagonal is greater than the sum of the row. And this is also called an SDD matrix. So you have an SDD matrix here. Let me call this matrix L. And what you're trying to do is you're trying to solve L of y. This is y is your vector is equal to b, where b is just 1 minus 1 and all zeros, right? This is for s, for t you have minus 1, and other is all zeros. And so this is a symmetric diagonal dominant system. Actually, this matrix is called a graph Laplacian. This matrix is called a graph Laplacian. Why is it called a graph Laplacian? It turns out if you take y transpose Ly, which is the quadratic form associated with that matrix, what you will get is you will get something that looks like this: yu minus yv squared divided by ruv. So you get a quadratic form, and this has connections to the heat equation in physics. And that's why it's called a graph Laplacian. So it's kind of a heat. The point is this is a positive semi-definite matrix because because of this this formula here. And what you want to do is we'd like to solve Laplacian, or in this case SDD systems. And like a breakthrough work of Spielman and Teng said that you can actually solve such systems in near linear time. And since then there has been significant work. I was hoping to actually talk about a result of Kellner, Orecchia, Sidford and Zhu from 2012, which give a very beautiful algorithm, very beautiful combinatorial algorithm to solve such systems. But I've run out of time. But these systems, I'll just say, so Spielman and Teng in, this is, I guess this is a while back, this is 04. And then there's Kutis Miller, Peng. This was 2010. And then there is Kellner, Orecchia, Sidford, and Zhu. This is in 2012. They all show how these can be solved in essentially O of m polylog n, and technically it's I should say that it's also log 1 over epsilon. So there's some precision issue. So if you want k bits of precision, you pay dependence on k. But these can be solved in m polylog n time. Now the graph Laplacian is going to be important, because when we talk about the Cheeger inequality and we talk about conductance, the graph Laplacian is going to make another appearance. So these graph Laplacians are sort of fundamental quantities that appear in many situations, and now it has, through this it has connections to max flow. And specifically it has connections to solving what is called the electrical flow problem. So this problem that I described is called, for obvious reasons, electrical flow. And again, it's this beautiful combination of beautiful things from ideas from optimization, which connect with things in physics, and then they connect with things in computer science and algorithms. So it's this amazing mixture of all of these areas. Indeed, the amazing thing is Spielman and Teng's result was, was a tour de force. It was multiple papers, many different ideas. And over time, people have simplified it to the Kellner et al. Result goes to the core and actually gives something that could be explained in a lecture, and actually proves that you can get an m polylog n algorithm to solve such systems. So essentially it says that if you're given this electrical flow problem, you can solve the electrical flow problem essentially in near linear time. So I'll end here and I'll take any questions that you have.